Welcome, everybody. I think we're about ready to get started. Our panelists are here, and we're here to talk a little bit about machine learning and some of the recent announcements by José and Dashbit and their impact on the Beam. So before we get started, I'd like to thank our gracious sponsor, Erlang Solutions, and to make an announcement that CodeBeam registration is still coming up. So you can register for free, and we've got some information for you here. And so here on this panel, this is not the exact right list anymore. We have a substitute. So my name is Bruce Tate. We also have Brian, we have Justin, and David is out celebrating his firstborn. Am I right? Is that his firstborn? And so Garrett is going to be joining us instead. So let's take a quick lap around the room and introduce yourselves. Justin, starting with you.
Hi, Justin Schneck. I'm co-author of Nerves Project and Nerves Hub. I'm currently a software engineering fellow at Very. It's a software consultancy, and we get a great opportunity to be able to apply Nerves Hub, Elixir, the entire ecosystem to projects for deployments in the embedded space. But we also have a great deal of people who work across many disciplines, including machine learning and back-end development, and the most exciting bits that I get to operate with and play with is seeing it all kind of come together, and not just the machine learning aspects, but Elixir backends and firmware development, and having it all kind of come together into one big concert that we can see producing these great projects that we get to work on and deploy.
Yeah, I can imagine things are pretty exciting around now. What about you, Garrett?
Yeah, hi, Bruce. Good to see you. My name is Garrett Smith. I'm a founder of a startup called Guild AI. We do tooling around machine learning experiment tracking and comparison and diffing. So I'm kind of sitting between the machine learning, classical data science, mathematics, and the engineering, and try to bring tools to the open source market that help data scientists and machine learning engineers develop models more efficiently. So the focus is on measurement, and so we have the tooling kind of reaches out and gets into both systems and the model performance across a bunch of different vectors. So I kind of see an interesting overlap of the data science / math and also the engineering side.
Yeah, it seems like the Beam has been all about for a long time being around the edges of that whole machine learning stack, and it's pretty cool to see that last little domino start to topple over a little bit, and we get to talk about that today. Thanks, Garrett. And what about you, Brian?
Hi, everyone. Hello from Berkeley, California, for all of those of you in the chat who are saying hello from your local area. Yeah, so I'm Brian. Some of you may have interacted with me as BLT online or seen me at conferences. I'm particularly obsessed with optimization games. So how can we build mechanical sympathy with the computers that we program? So I've done a lot of work in Erlang. I've done quite a bit of work in systems programming languages recently in my career. And I've been working in data engineering or infrastructure support for data science groups lately. As this sort of like subfield has exploded, that's definitely been a thing that my specialization ends up supporting. So in some sense, I'm a little bit of the wild card panelist, and that I am not a machine learning engineer, but I am very interested in how to make programs run quickly and run well. So yeah, looking forward to fielding everyone's questions and being a little ignorant about it. Bruce, how about yourself? What are you up to?
Thanks for not forgetting me, Brian. I am at a company called Groxio Learning, and we actually teach the Beam, mostly OTP and LiveView, but we also kind of knock on the door of a lot of different programming languages. And recently we've been spending a lot of time in the Julia space, where we've been kind of talking about the Julia data science stack and Flux, which has some of the goodies that José and Dashbit have kind of been working on at with the NX library. So we get to talk about that. So I'm really excited to talk to each of you today, because it's a cool story, right? We have been in Beamland, we've been kind of surrounding this whole machine learning area, so that there's this whole thing about the data wrangling that you have to get right. You have to get the data, and you have to have the framework to take it apart cleanly and sample things cleanly. You have the Internet of Things with Justin. You have kind of the knocking on the doors and right around the edges with Garrett's company. And so it's kind of exciting to see that we get to start talking about that last domino in the middle. So the first question I'd like to throw out to the panel is, what is this machine learning anyway? Maybe start with the data. What does it mean to have data that's ready for a machine learning application, and why is that significant?
This is a race condition. This is classic race condition. Some kind of distributed lock. Bruce, are you our lock? You're gonna have to call on someone.
I think I'm here. Can you?
Well, I mean, I can certainly chime in to start here. I mean, it's really kind of the 80% problem in machine learning, maybe more. There's nothing, you can't really do a whole lot in machine learning without data that's learnable, and that's a problem, a whole sort of field of problems. So the infrastructure that is required to do this in the wild is considerable, considering data as a generic problem. And there just isn't a single shop that does machine learning that doesn't have a humongous investment in data, data processing, just moving data around, and then you sort of inch into the general problem of engineering your data for learning. So there's cleanup, there's feature engineering, there's all sorts of different methods for training, test, validation. So it's a really big topic.
Yeah, and so Justin, you've been working with Very Possible and the Internet of Things, and kind of one of the on-ramps to establishing data is this whole idea of sensors, and how do you get those close? And you've been involved in launching companies that are all about getting sensors close to important things to measure in the field.
Yeah, no, that's interesting. Well, I mean, data is just one aspect. Like it's like the influx of the beginning of the problem, right? When you get your hands on most amount of the data, then you can start working on churning through it and being able to do something productive with it. And on the whole, when we talk about what is machine learning in general, I almost like focus there directly on it being this like mystique, right? That a lot of that like is like falls upon lots of developers, right? And it's interesting because when people talk about machine learning, like when I joined up with Very, I started coming up in contact with a lot of data scientists and learning how to communicate together with data scientists and like speak similar languages so that we can kind of be effective across disciplines. And I had this feeling where I was just sort of taking what they told me as to be like the end all be all truth, right? Where it's just like, yes, whatever you say, I don't understand these things that you're talking about, but they perform this magic and this mystique. And it was funny because with IoT we see the same thing with people with hardware, right? It's like this same situation where when we introduce people as engineers to firmware, they're sort of led to this mystique as well, where they see this piece of hardware and they think that it's like infallible, and that it was built by smarter people than me, and so therefore it must also carry this like truth mystique. But that aside, yes, you asked about sensor data and amassing a lot of that, and it is very interesting because yes, on the flip side of things, from what we're used to as this cloud data architect forward sort of approach that a lot of us as developers feel. On the other side, we're entering the Internet of Things, where sensors are becoming more ubiquitous in our lives and are trying to be able to stream more and more data. And amassing that is very important. And we're sort of caught in this contention, I feel, where we want to be able to surface the data, but the data surfacing is expensive, especially in the case over wireless connections, right? And then in those cases, what we usually do is take that juicy data that could be so useful for producing quality machine learning models, and we turn it into the model so that we can stop ourselves from having to stream so much expensive data, right? It's like this weird self-fulfilling prophecy of a problem. But yeah, we've worked in several situations together so far, one of which that's notably is we see a lot in the industrial IoT space, where a lot of this sensor data is coming from mostly industrial machines, warehouse automation, and things like that. And as you can imagine, due to side effects of unfortunate circumstances of COVID, that industry has sort of been seen in a light where they realize that they're behind, and that we need to be able to implement more of this automation so that we can operate our facilities in safer, less dense packed ways, but effective outputs too.
Yeah, so we're knocking on the door now, and then so we want to have this data feeding into a model. And we want to kind of iterate on the model for a while. Rather than having a function that is purpose-built for a project, right? We have a function with lots of knobs and levers that you can configure, right? And that's kind of the L in machine learning. So so now we kind of get into this place where Elixir needs to be good at something that it's just not. Erlang needs to have something that it just doesn't have. And so those are some of the things that are missing in machine learning. So so enter the announcement that we had a couple of what is it, 2 weeks ago now? I can't remember. It seems like a long time. But what are some of the things in that announcement that caught your attention? Brian.
I think what caught my attention. So if I sort of put my infrastructure hat on, when I look at an organization that's trying to do machine learning, there is the sort of excitement around the machine learning bit. There's a little less excitement rather around the data engineering bit. And there's almost no excitement around the data collection bit. Data collection gets farmed out to new people. And at each point in between those groups, there's some sort of interface that has to manipulate the thing going this direction. The problem that I've generally seen in organizations, especially as they get larger, is that the collection is an IO bound problem, and they will be working in languages that are suitable for IO bound problems or with technologies that are suitable for that. And then it gets narrower and narrower and narrower. And at each junction, you switch languages, you switch jargon, you switch ability to talk back and forth with one another. I've definitely worked on projects that you would sit in the data engineering middle there, delivered a whole thing, and then found out when it actually got to the machine learning people that because they couldn't read our program, it was just trash. It was very expensive trash, and we delivered it very nicely, but it wasn't usable, in part because the tiny sample that we were able to produce as a proof of concept was not indicative of the total set. So what really interested me about, so kind of the holy grail is, can we have a consistent vocabulary and jargon back and forth across that whole pipeline? And the big limitation, so Beam stuff historically has worked really well for IO bound things, but then when you got to do numbers, you stop, right? Can we do that now is a very interesting question to me. And I'll be very curious to see what happens at that machine learning side of things.
Which brings us to that first announcement, right? So there's this idea that we have these arrays that, are work pretty well with functional algorithms, but In machine learning, we have tensors where we have to basically deal with them in bulk. And it's not just one dimension or two dimensions, but sometimes many dimensional data. Very large data sets that have to move very, very efficiently, sometimes with specialized hardware. So can anybody talk a little bit about the idea of the NX tensor and the abstractions around it that allow us to do things like, oh, I don't know, matrix multiplication with a low-level operation rather than the typical enum or reduce libraries that you'd see?
Yeah, I mean, to Brian's point, if you're working in Elixir today, I mean, I guess 2 weeks ago, you didn't have any option. You really didn't have any option at all. And you're forced into a translation scenario. And that, from a system standpoint, in computation is quite a nightmare because you are dealing with moving huge amounts of data through a pipe just to compute it. And that's going to be a problem in any environment. And if you happen to be using Elixir, and of course sitting on top of the sort of the distributed powerhouse of the Erlang Beam ecosystem, there is a tremendous lever there to do distributed compute. And if you look at I would say the classical environments for doing this kind of work, it's C++, it's Python. And there's a lot of systems that are I would say, I would not be comfortable with them operationally. I wouldn't, but that's not to say they aren't being used operationally, but people have different comfort levels. So that's a big problem. And I think addressing the compute, at least getting on a track to address compute and getting on a track to build out distributed computational libraries, similar to what you would see in the Python ecosystem, I think is potentially a huge game changer for organizations that want to have sort of the best of both worlds with robust systems-oriented application development without having to deal with really the technical problem of getting data through these little compute pipelines as you need to operate on them. I think as a general platform, the Elixir with this extension could potentially be extremely compelling to an organization.
So it's interesting, Garrett.
Sorry, go ahead, Bruce. I want to hear what you have to say to that.
No, go ahead.
Oh, I was going to focus in on what Garrett was saying regarding the idea, like as you were mentioning, with being able to handle IO bound problems really well. The Beam's really good at this, and being able to have this venture into processing numbers that we would normally have to go outside for. The IO portion of it, I've always saw the Beam as being exceptional at handling control plane, about the orchestration, the transformation pipelines, the ability to flow the information through and react to failure conditions due to the process modeling of those kinds of things. That's why we love and heavily advocate its use for embedded state machine designs. And it's funny, as we were starting this, I kind of talked about the illusion of or the mystique that is this, and it's kind of the idea that machine learning is this giant umbrella. And as we're talking through this, we're making it clearer and clearer that there's all of these different alleyways that you have to be able to go down, all of these different subset problems that make up that entire system as a whole. And having that effective control plane means that we can efficiently move the pipelines, but not be able to necessarily process them, right? And as we're saying, we have to reach outside for that kind of thing. We have to reach to some other language, and mainly because, as we were saying, if we zoom in on the computer, on the hardware itself, there's massive amounts of data, and these pipelines are literally like trying to be able to move it through the processor, through memory, through fast access areas, so that we can be most efficient at these kinds of operations. And the very interesting aspect that I believe NX gives us in this case also is that we're given this ability to be able to process these kinds of tensors, these kinds of numbers, and these kinds of efficiencies, because it's giving us this window into that external world where that memory, that carve out of acceleration can exist, but we can see it opaquely in our pipelines, and we can control it from the external portion of it through this backend compilers mechanism, right? And so So like that abstraction that it was built upon at its first layer of the XLA compiler being sort of the first of potentially many backends that we could expose through this mechanism. That right there is interesting, because we now have this abstraction that gives us a building block for being able to give us a vector into the outside world in an accelerated way, not just for numbers or tensors.
Yeah, that sounds like it really starts to tie together the architecture of the Beam and the architecture of the Elixir language and the architecture of NX to kind of start to really move the ball forward beyond where we are now, right? Into the new GPU the GPU models on the desktop, or the purpose-built chips on the cloud, or in the Internet of Things, and that's a really cool thing. So there's one more announcement that I want to get to before we open up questions to the panel. So just to kind of review where we've come from, we have this data, and we've got to like grab it and prepare it, and then we kind of feed it into this model, right? And the model is not like a purpose-built thing that computes, the color of the moon or whatever, I don't know, whatever you're computing. It is a model with all these knobs and levers. That's a general purpose function that we feed to, we feed a training algorithm in. But then there are these 3 steps where we have the training, and then we evaluate the loss. And then based on that loss, we make optimizations of those knobs and levers, right? And the optimization, or the evaluation step that José announced, was that we could take a loss function, and we could translate that to basically the speed of change, differential equations that, derivatives that could basically give us the trajectory of how bad a model is getting, how fast, and then we could flip that on its head, right? So why was this such a big announcement? This AutoGrad or auto diff? You want to take that one, Garrett?
Yeah, I mean, I think it's sort of part of the bigger picture, which is the ability to do optimization on important computational algorithms. In this case, it's part of gradient descent, which is part of almost every standard learning algorithm. So it's really, any kind of differentiation is inherent to most machine learning methods. So I mean, I think that fills out the story. I do think, though, that we are talking a lot about machine learning, and I kind of, as I was thinking about it, I'm thinking about it a little bit in terms of generalized compute, and there is a really, really large ecosystem of existing models, training algorithms, frameworks, etc., in other languages. And it's not clear to me that just because you can do it in Elixir, everyone's going to start to do it in Elixir. But to be able to do any kind of computation efficiently with large data sets gives this community the ability to start to build out frameworks and libraries and other things. So I think having optimized operations, the way they've exposed it currently, is a good example of many things to come. So that as a platform, as an architecture, those who are building libraries can go ahead and implement these optimizations as needed. So I think it is critical to most machine learning methods, but I think I look at it more as filling out kind of this template. This is where the tech is going. The approach that José and his team is taking, I think, is a good one. And I see this as an early stage, almost a proof of concept. I'm really interested to see where the community takes this and how that evolves.
Yeah, I think to sort of add on to that, I've been spending a lot of time reading papers about just how to structure data on disk, if you can assume that disks are very fast in sort of random access. And a recent-ish trend has been learned index structures. So basically you start to inject very simplistic like neural nets or other machine learning approaches into these structures to build out your index. And in some cases, they have just absolutely outrageous speed ups for some workloads. Now, if your language can't express those, you're going to get left behind. You've got to be able to have the pieces in your base language to be able to express these types of computation. So that just popped into my head, Garrett, while you were talking. Absolutely. These are just the pieces that we're probably going to need in languages moving forward as we just start to assume that they're there.
It couldn't be a better example of the type of thing doesn't pop up as a traditional machine learning application, but it would in this particular case. So I think it's where having this, and you can just forget about kind of the big AI story and look at it as, hey, what can I do now? And Brian's example is really great. And I'm actually surprised to see how long it's taken CS in general to be using these things. And a platform like this within this distributed environment, I think is going to be a really great laboratory to start to build some of this stuff out.
Yeah, so there's a great comment on the chat that I want to read and get some comments from the panel. I think the beam is special because we're all so used to thinking about data as not something you can move from place to place for free. And every other ML framework I have seen has not had the mindset to think about that important problem, which is truly important for ML. That's interesting.
Yeah, I think I read that before, and it struck me. I wanted to comment back in that case about that answer, because as Garrett and Brian were saying and alluding to, like having these things become more apparent, that it's ubiquitous and that it needs to be there for future programming languages is starting to also become clearer to me. And it seems that ML frameworks and a lot of the mindset mainly focuses on a lot of the training portion of the problem, and which is very expensive and very tedious and understandably difficult, and therefore a lot of the tooling and the data movement needs to be optimized for that portion of things. But when you think about where it's going to be used, inevitably, you need to be able to perform optimizations to be able to deliver to that location, and you need to be able to continue to iterate on your designs and test for those locations as well. And as you were mentioning, usefulness for these kinds of applications, right? And how common they could become. I mean, the practicality of them, really, in the case of just a subset of machine learning as far as neural networks is concerned, can really be useful in the case of providing new types of sensor input. We see this in the case of industrial IoT designs for factories. You can clearly and easily create electrical logical sensors for like common, easily testable things that can give you logical binary feedback. The kind of feedback that we as programmers are already used to programming against, building logical structures and handling and reacting to. But there's always this guy that works at the locations that can look at a machine and give you like that's probably going to fail because I've seen this stuff for so many times, or I've seen this before. He himself is like this irreplaceable sensor that you can't really like model in some way, because the predictability is based off of these probabilities, right? And that's what we're given now with this new addition. Like that's why this is so important for languages and frameworks to embrace this as a new normal, is because no longer are we bound to just being able to solve programmatic logical problems, but we can intermix now logic with probable output, probability. That's the machine learning aspect that is really interesting to me, is because it's this new brush that I can paint with now.
Yeah, that's an excellent take, and I was thinking very much the same thing as when we invited you and the work that's happening at Very right now. It's kind of goes hand in hand. There's a great comment by Kenji Rikitaki, and he said that machine learning is a huge numerical processing field. I'm curious if NXLA will become a new standard for at least the basis of a standard for numerical data processing. numerical data processing, not only limited to machine learning, and this was the point that you made earlier, Garrett, but also for other interesting problems such as digital signal processing and almost anything related to statistics or math.
Yeah, yes. So the XLA gives you access to the ecosystem of accelerators. It's a profoundly important technology. So that languages are taking advantage of it is really a big deal. And so yes, all of that. And I think that's, to me, that's actually more likely the trajectory that, where I suspect if I had a bet, I think that this would go. There is a certain amount of momentum that exists within machine learning at large. And keep in mind that machine learning is driven by data scientists. And data scientists are using Python primarily, some other languages. And to tell them, hey, check out this new language, it's not going to happen. But people who are building systems and doing, these difficult problems are going to, I think, be driven to look at the Beam and the Beam architecture and the ability to basically drive XLA with it, which is really, really sweet.
Yeah, so there was a good question by Jim Fries. He's asking which companies on the panel were actually using machine learning.
So I just recently switched companies. So and I have promised to the community manager at Datadog that I didn't know anything to talk about. My previous company, however, did. So I worked for Goodwater Capital, which is a small venture capital firm. And its main differentiator is that it's machine learning as venture capital. So that's just how it operates.
So Justin and Garrett, I know you've answered this question, but just give us an interesting problem that you're interested that has piqued your interest as you look at these announcements.
I found that it's become more apparent that our clients they're either asking for machine learning services or they're not asking for it, but don't know that they need them. And one specific one was for an intrusion detection system for network traffic that would monitor your network. In that case, the problem itself on site was very much so in tune with this kind of application for machine learning. And it's also interesting to be able to note as well that from what we've seen, there's a common misconception that machine learning is all about neural networks and very specific subsets. But as mentioned as well, being that this is an opportunity for us to be able to accelerate any kind of statistics or mathematics, there's a lot of machine learning that can be done quite simply. And as we've also seen with other clients where we're just sort of not doing very intensive predictive things, but still setting up constructive pipelines.
And what about you, Garrett?
I mean, there's a lot of applications of machine learning that are underexploited because of the engineering difficulties of doing real-time compute on massive data streams. Not even massive, just real-time or near real-time. So I mean, something like security application, anomaly detection, where you're processing streams of data in real time, and you may be retraining models in very soft real time or near real time. This would be an application that would not require necessarily any fancy mathematics, but it would require a pretty careful balance of distributed systems development and compute, and has been sort of talked about. That's difficult. I wouldn't say that I wouldn't say that there aren't frameworks that are doing this. I would say that anyone who's doing machine learning at scale is dealing with the problem of moving data around, whether it be from resident RAM to GPU memory or CPU memory to that pipeline. That's a big problem. That's got a lot of people working on it, and just moving data around networks. So people who are doing it are doing that. The one thing I think that is also underexploited or underaddressed is the problem of reliability. And when you build a system, of course, the system needs to work for any given definition of work. And the technologies out there are really scary in terms of that topic. I would love to see the sensibilities of the Beam community brought to bear in this area, because I think it is, I never hear it talked about. So this is the one thing I would say is not talked about, would be this problem domain in the context of building reliable systems that work. Work
Yeah.
well under duress. Let me qualify it that
way. This reminds me of a fun application story that I heard once. I was at CraftConf in Budapest in 2019, and there was another speaker that was there, Pamela Gay. She was from the Planetary Institute, and her and I got into a wonderfully fascinating conversation on the side stage at one point about the applications that she's investigating, or the Planetary Institute is investigating, of machine learning applications towards an upcoming mission that they had, where they were trying to be able to map an asteroid to identify a landing site that would be, safe for their spacecraft to be able to land on. As a small tangent, which I'll take, Perseverance has recently landed on Mars and had instrumented a very similar technique for its landing systems as well, and that it was able to, on board, capture image data coming from the underside of the rover, and as it was descending towards the surface, it was able to find and identify, based off of performing some machine learning models on understanding and measuring visually the size of obstacles that were existing on the ground, to find a place that would be the smoothest, right? And to tie this all together, then basically what the problem that Pamela was suffering from was that in order for them to be able to build the model that allowed them to be able to, this was their goal, was to build this model that could exercise this actual descent of the spaceship into the safest area on the asteroid. Well, they needed to roll that all the way back into the data processing portion of it. That meant that they first had to build an engaging experience for community, people in the community, to come in and being given photographs, mark lines in the photographs that would effectively mark the edges visually of rocks, right? Because this was the product of the data that's necessary to feed the machine learning training systems, so that it can start to be able to build the picture that it needs to be able to make the proper predictions. You have to give it positive data sets so that it can understand what it's trying to learn, right? So it was just a fun conversation, as thinking about. I don't know about others here, but one of my fascinations would be to be able to get something into space, and seeing that application would be wonderful if we can have Elixir doing some processing on systems like that.
So Jim has another question. He asked, what does NX have numerical libraries, or is work being done to develop standard numerical libraries, especially things like matrix math and so forth? So I know that there's some early work underway. Who wants to take a shot at that one?
I'm not qualified. From what I've seen, it's very early, and the goal is to develop things like they've cited NumPy and JAX as sort of architectural blueprints to follow. So I would expect something along the lines of the NumPy, so which would be driven centrally by a data frame type of implementation, and then all sorts of never-ending compute and query capabilities on top of that. That would be a guess. I would ask José that, though.
Yeah, I agree. We're really early on that front.
I'm very much so interested in seeing where that goes, though, really, because I'm not going to say that they've done it right and that blueprint is perfect. And it's a good one to follow. It's one that we have. As far as NumPy and implementing other libraries, the part that I'm concerned over a bit is just obfuscating a little bit of in this realm, especially obfuscating what's occurring under the hood, right? And like, as we talk about layering more libraries on top of things to be able to make it easier for more and more programmers to be able to have access and maybe at a higher level have understanding of these things, I feel like in this field, it's very easy for you to shoot yourself in the foot when it comes to like tuning these parameters. Like it's very valuable to be able to have that deeper understanding. So I hope that we can take this as an afforded opportunity to be a little bit different, and maybe question some of the structures or how many abstractions get layered on top of things.
Yeah, so I think that there were a couple of talks that were really interesting, and I think that they were in the very early days of Elixir, right? So José gave this talk called "What Elixir is About," and he was talking about the abstractions that we were building on top of, right? And then probably 3 or 4 years ago, not sure if it was that long, but he gave this talk that Elixir is done, and basically not to say that Elixir is done, but to kind of signal that the development, open the floodgates, right? The development, come on, step in, the water's fine. Now we're going to move the innovation to the libraries around. And it kind of also strikes me what happened with Plug. Essentially the whole move was to establish a toolkit for building web servers. So I think it's great strategy. It's early strategy, and I'm not sure where things are going to go. Let's see.
Splitting it apart. Plug, that's a very good one. Composability, that's what I love about Elixir, really. It's like, it's so easy to be able to just compose things in a way that makes sense, and like the Unix way, right? Like how José says as well, like flow and such. Broadway, we're not part of core. It's very difficult to be able to just there's a high bar for what gets put into the core of the language, and as NX and XLA are spun off onto the side as well, it just goes to be able to show that further. There's deep focus on these different subsections on what they're good at, and that the composability between all of them is what's really beautiful when it comes together.
Yeah, here's another one for you, Justin. It's while we're getting fat paychecks from solving real problems in data science jobs is great. I think we all agree on that. I think that we're all wondering when we can get speech recognition for nerves, for my nerves project, so I can get an onboard voice control for my Raspberry Pi. Bonus points for voice synthesis, Justin.
Yeah, obviously the best problems to solve are ones where you can synthesize voice and have it say things for you. This shines a light on a tough part of this problem that I deeply feel, which is exercising some of this stuff, performing inference on models on edge devices like Raspberry Pis. There's not a lot of resources on these devices. Right? When we look into what's available on the market, I mean, Raspberry Pi has become quite powerful, but it's mainly starting to be able to, as the market with mobile phones has been dictating and become a lot more gracious with its CPU, and the GPU itself is getting better, but there's a lot of other ones that are out there that we see that have these more GPU-centric offerings. NVIDIA, for example, has a series of devices that are called the Jetson series, and it's effectively an ARM 64 processor strapped to a NVIDIA graphics card, right? And we kind of the thing that I've identified in this case is that that's kind of like the answer in the market right now. If you need to be able to perform this kind of stuff, like a lot of the community is caught up in being able to build and train very large data sets, very large models, because they want them to be precise and they want to measure them so that they perform very well. And in the lab conditions that are in the cloud where you have massive farms to be able to operate on, that's fine. But when you have this tiny little device that you need to be able to make it actually get exercised on in the field, it's not fine. It could take a long time. We've seen facial recognition, like Python-based facial recognition ones, running on the GPU on edge devices like Raspberry Pis and stuff, operating under heavy loads at like maybe 1 inference a second. You're not really going to be doing very high-end video pipeline processing with precision on those in those locations. And so I think that this is a blend. We need to be able to see, we need to be able to more properly leverage all of the assets that are available to us so that on these low power, tiny compute devices, we can be very efficient with them. But we equally need to clean up our mess when it comes to the inefficiencies or the amass that we've created with these data models. And that also produces the need, the sort of circular need to be able to accelerate the training aspects of them so that we can very quickly test. You know, like Elixir made testing a first-class citizen. It kind of broke free from the model that Rails and Ruby developers were used to, where tests would take a very long time, and then or other languages where it would take a long time in CI to spin up. Like we wanted that to be fast, and then we kind of got that, and that's what we're going for with the NX route as well. And so the market isn't quite ready yet, because what NVIDIA is offering is effectively like it's great. It's a standard. It runs commonly to the desktop machines, but it does run pretty hot. And I believe that there's newer pieces of hardware that are on the horizon that are going to give us the ability to accelerate these kinds of things. But in a way that might be a little off the beaten path. It's becoming clearer that we're not just going to have to target for graphics processors a NVIDIA backend or an AMD backend, but we're seeing a lot of these like tensor processing units, these ASICs that are coming out that are very specialized to only running neural networks. And each manufacturer is going to have a different kind of way to be able to get the data into that processor so that it can run efficiently, which is also what makes it really important for us to be able to create these robust and steady pipelines so that we can have confidence in deploying to these devices and building confidence that what we train in the data centers will actually be able to operate efficiently on the variety of targets.
Yeah, I think that we're getting pretty close to a time to wrap up, but I'd love to take one more lap around the room and to talk a little bit about frontiers for the beam. Where are we going? What's the low-lying fruit? What is the low-lying fruit? You want to get us started with this one, Brian?
So my Zoom has been crashing, so I actually missed all but the "Would you like to get us started, Brian?" If you could.
All right. So we're going to talk about frontiers. We'll let you take a pass on this one. Justin or Garrett, you want to take a crack at it?
I mean, I was going to ask Brian what he thought.
Now, I mean, now that I'm filled in, I actually do have thoughts, but go ahead, Garrett.
All right. So, I mean, in the context of this discussion, I think that before we get into frontiers, I'd like to see one of the problems I think is going to be that the expertise that we have in the Beam community may not be driving some of the machine learning, aspirational goals here. So, are we going to get a NumPy library? I mean, are we going to get the sort of the equivalent that what exists in the Python ecosystem in Elixir and NX? That will be very interesting. It's a fantastic amount of work and will take a lot of people with a lot of experience, a lot of skill. I think what will be interesting is to see, along the lines of what Brian mentioned, a very tactical application of this to solve more traditional CS problems, and maybe start to use the word compute in driving these things, and back off of ML a little bit, because I think that will open up a lot of very, very interesting applications that will absolutely cannot be built without this. So I think that could be a frontier, but I think it's, it will, I'd love to see what is next in terms of applications that will be built on the near-term libraries that come out of this.
Yeah, so I definitely agree with the notion that there are just an entire class of problems that we don't really solve today because we don't have the basic tool set to solve them. Like the learning indexes that I've been reading about are intentionally extremely simplistic so that they can be implemented in languages like C that, are not really amenable to this type of work. And also to just get people who are not traditionally interested in these types of algorithms to realize that they can work for non-traditional applications. I think the other thing that strikes me as a frontier is I think about the old, or not old, I think about the current, but cell tower deployments of Erlang, where it's just sort of like a box that goes into a cell tower and then it just keeps ticking over. And if one of the pair computers dies, it sends out an alert. Computing at the edge is going to be the big theme. So processors are not really getting faster. We are getting more of them. Networks are not really getting faster, although we do have fiber coming on more and more. But there is fundamentally a limitation to how much data you can ship to a central place to have it processed. So then the question becomes, how do you start to distribute that computation? And I think the beam is sort of ideally suited for edge computation where that edge can't ever go down, or it has to go down in known predictable ways. So those are two future avenues that I think are very interesting to me.
Yeah, edge compute. Oh man, I've definitely been obsessed with this for over the last year and a half. Bruce, when I saw you at Lone Star, I was sort of a little on fire over actually a little on fire over a talk that you gave several Lone Stars ago from that regarding you discussed programming sort of in this means of a pendulum and technology, much like fashion coming in and out of style. To where we've swung in one direction now where we've seen this we've seen this shift of the cloud becoming unsustainable, now swinging back into the other direction where we need to distribute the load across the network and get it to different places because we literally can't, we're running out of air, not space to cool these kinds of things. So why not distribute them to places where there's more air, right? So I think that all of this tying together, because edge computing is my obvious fascination, but all of this tying together to where then the thing that really fascinated me in the beginning about Elixir was its capabilities of doing metaprogramming, and I see this solution of our data traffic problems back and forth, having to send lots of data over the network back and forth. Can in a way we can sort of, I'd like to see us leveraging aspects of machine learning to be able to sort of digest this into a smaller subset so that we can be less wasteful and we can in a way metaprogram the communication of data that we have from across mass distances to make that edge compute network even more robust and reliable.
And I'm going to say I agree with Justin for the most part, but I'm looking for the deep learning types of things where you could train most of a model somewhere else, and then actually put the user interface into the hands of the edge, whether that's voice, gesture, facial recognition, handwriting recognition. I think that all these become approachable problems and embedded problems. And I think that the beam is a natural place for such things to live. And I don't actually think that you have to have NX or any of the new libraries everywhere. I just think that you have to be able to build a model efficiently somewhere in the stack and get the pretty relatively simple working model out to the edge where you can do something with it. I think that's what it's all about. So let's see, we should say, let me share screens real quick. Sorry, I'm having Zoom difficulties for a second. All right. So I'm going to share screens and wrap up. Okay. So I want to thank our sponsors and invite you to come join CodeBeam CodeBeam Virtual. It's coming up. There's a 20% discount for the registration, and we have group tickets available also, so you can come check those out. And a big thanks to the panelists, Garrett, Brian, Justin, and congratulations if you're listening, David. And thank you so much to the audience for being here. We've really enjoyed talking to you today. Thanks.
Thanks, Bruce.
Thank you.
Thank you everyone for coming.